Welcome everyone to the ACOM seminar. Today it's my pleasure to introduce Dr. Kevin Cossel from the NIST Fiber Sources and Applications Group here in Boulder. Kevin received a dual degree in physics and chemistry from Caltech and then came to graduate school at Gila to pursue a degree in chemical physics. At Gila, he worked with Jun Yi and Eric Cornell on developing broadband direct frequency comb spectroscopy techniques and high-resolution spectroscopy with molecular ions. Kevin then joined NIST in 2015, first as an NRC postdoctoral associate, and then staff, where he works on atmospheric measurements using dual frequency comb spectroscopy. As part of this work, he received the Department of Commerce Gold Medal for his work on comb-based spectroscopy and a Colorado Governor's Award for work on detecting methane from oil and gas infrastructure. Today, Kevin will be talking about constraining greenhouse gas emissions across spatial scales using long open path measurements. And before starting, I'd like to remind the people following online that you can enter your questions in the space below the video at any time during the talk. At the end of the presentation, I'll read those questions to Kevin. And so Kevin, it's yours.
All right, thanks Kyle for the introduction and for the invitation. So I'll be telling you about a few projects that we have in constraining greenhouse gas emissions across sort of a variety of spatial scales using long open path measurements. And this picture is from a field campaign that I won't actually talk about, but it's a nice picture anyway, where we did a collaboration with the Colorado Department of Public Health and Environment. So our instrument was located in this van over here, and then the CDPHE Camel mobile lab was in that trailer there. So, of course, we all know about greenhouse gases. And, what I really want to point out is that in order to really understand what's happening and in order for policymakers to really have a good, targeted ability to, impact greenhouse gas emissions, we need to have measurements that look at sources across various spatial and temporal scales. And because, greenhouse gases are prevalent everywhere in the atmosphere, we also need to be able to do kind of accurate measurements looking at very small changes on a background. And so I'm going to tell you a little bit about our technique for doing that, which is open path dual comb spectroscopy, and a little bit why we do this, and then look at some applications, and then wrap up with kind of where we're going with this technique. So the heart of the system is a laser that's called the frequency comb. Basically what this is it's a laser that outputs extremely short pulses in time at a very well-defined rate. So you see these short pulses coming out, and then a time later there's another short pulse. And each pulse is coherent with the other one, with the previous one, which means that the electric field at one time, if you know the electric field at this given time, you can know it later on. There's no real noise between those pulses. If you looked just at sort of one pulse in time and took the Fourier transform of a short pulse in time, it would be a broad optical spectrum. The neat thing about the frequency comb, though, is because all of these pulses are coherent, you can look over a longer duration of time, Fourier transform that, and you get this broad spectrum, but it's composed of many, many individual teeth. As you look longer in time, basically those teeth get narrower and narrower, and they look like delta functions. And all of these teeth cover this broad spectral range, but they are at kind of well-known frequencies, which are basically just defined by the rate at which the pulses are occurring in time, and then one other offset frequency that's easy to measure. So if you know, the frequency, if you know these two frequencies, you can map basically all of the frequencies of all of those individual teeth. So this gives you a very high resolution spectrum with basically extremely accurate wavelength axis that covers a broad spectral range. Now, if you want to use this for spectroscopy, you could take one of these frequency combs, you shine it through some gas, and you measure the absorption at different wavelengths, different comb teeth. But you need a way of actually resolving all of these individual comb teeth, all of these individual modes. Otherwise, you just sort of smear out the spectrum, and you're limited by whatever your spectrometer resolution is and lose some of the advantages of the frequency cone. So our technique is called dual cone spectroscopy. As you might guess, it involves using a second frequency cone. So we take a second frequency cone, and what we do is we have those two at very slightly different pulse rates. So one of them is pulsing at a rate shown here, and then the second one pulsing at a slightly different rate. And if you look over time, those two pulses from one versus the other laser will sort of walk across each other. And this looks basically exactly like a scanning Fourier transform interferometer. Right? You're just changing the delay of one of those pulses, one arm of that interferometer, relative to the other one. So you mix those two together, and they give you an interferogram, much like you would get out of a scanning delay interferometer again. But that occurs just repeatedly over time and with no moving parts. You can Fourier transform that, and that gives you this nice mood-resolved spectrum. And so we kind of maintain this broad bandwidth, this high spectral resolution, but because we're sampling it at this well-defined grid with really narrow points, we basically have no instrument line shape. So unlike a scanning Fourier transform interferometer where your instrument line shape can change over time and is dictated by how far you can scan this one arm in your interferometer, we basically have completely negligible instrument line shape. And we can do these measurements very rapidly. So we get one spectrum in sort of millisecond timescales. Signal to noise on that one spectrum is not particularly high, so we have to average for longer to be able to measure small changes in absorption. But you know, we can get this sort of varying temporal resolution. And then we use this for open path measurements. So this is a picture of two different measurement paths that we've done from the NIST NOAA campus in Boulder. So this is NIST here. We had our lasers up in a lab kind of on the top floor. And then measurement path over to NOAA, that's kind of 300 meters away, one way, and then up to the hillside called Kohler Mesa, that's about 1 kilometer away. And what we do is we take these frequency combs and we connect them to a telescope, and we make the laser beam a little bit larger and send it out to this retroreflector, which is basically 2.5 inch to 5 inch diameter, 3 mirrors in basically the corner of a cube. And so it sends the light back directly along the same path, regardless of the angle of the reflector. And then we measure that back at the telescope over here. And this gives us, because we have a laser source, the ability to measure over these fairly long paths, so kilometer, multi-kilometer scale paths. The open paths gives us the ability to do this, to have kind of a spatial average of the concentration. And so we're not as sensitive to small variations in wind direction if we're trying to measure a source, or we're not sensitive to small sources that happen to be really, really close to your point sensor. If you had a point sensor right here and a car was idling outside, you would start to pick up that. And so this spatial averaging kind of gives us the ability to measure more on scales that are relevant for, say, atmospheric models. And then, open path, we have no biases from sample lines and tubes. This is what this looks like in practice. This is our spectrum over 1 kilometer or 2 kilometers of air out to that 1 kilometer path and back. In the near infrared spectral regions, kind of 1.6 microns or 6,200 wave numbers. And what you see is a bunch of narrow gas absorption lines on top of this broad background, which is the intensity of our laser source. So we have various ways of fitting out this broad background, and then look at just the gas absorption, and then we can zoom in on a couple of those lines, and you see kind of how well resolved we're sampling those features. And then we do a fit with a spectral model from Hytran or something like this. And in this case, we were fitting multiple bands of CO2 and one band of methane, multiple lines of water. So we were fitting kind of hundreds of water lines and thousands of CO2 and isotopolog lines. So just real kind of quick, a couple of applications that we are looking at, and I'll talk about a couple of these more, but looking at sources that are distributed sources, so agricultural sources. We've done measurements, I won't talk about this one, where we put that reflector, instead of having it in a fixed location, we put it on a UAV and we tracked that around. So you can do kind of more rapid flux estimations and spatial sort of inhomogeneity measurements. And then we have the ability to measure some VOCs. So that was the picture at the front as well, where we went to an oil and gas drilling and fracking site and had multiple beam paths measuring VOCs there. And then looking at kind of regional emissions and pushing towards looking at air quality as well. So the first application that I'll talk about in a little bit more detail is continuously measuring emissions from cattle operations. So if you look at the EPA greenhouse gas inventory for the US, two of the major sources, this top one, enteric fermentation from cattle, but then also cattle operations contribute to this manure management. So, the dominant methane source, according to the inventories at least, is sort of cattle in the US. Now there's a question, of what goes into this inventory and how accurately do we actually know these sources, and then, what can you do about these sources? So you need measurements to really look at this in more detail and verify this inventory and look at how things might change in different areas. And right now, for understanding cattle emissions, what's done is basically all measurements in feedlots. All right, so cattle spend some of their time in feedlots, and these are a little bit easier, although large feedlots are still hard to measure with point sensors. What's usually done is measurements happen for a little bit of time at a feedlot, and then those emissions values are scaled up to the inventories for the entire country. And there's a lot of uncertainty in this. And another source of uncertainty is that cattle also spend a reasonable amount of their time grazing. In some cases, it can be 75% or more of the cattle lifetime is grazing. And this is extremely difficult to understand with traditional sensors, because you have cows that are now spread out more, they move around. And so the contribution of this to the inventory is really not as well known. And then there's also interactions between the animal diet and the animals moving around and things that might happen in the soil. So there's some thought of there being a microbial sink, and it's really not clear how large that is or how much it changes when the cattle are present. So we want to be able to do measurements kind of in both of these areas. And so the first step is that we wanted to compare our open path measurements against kind of a standard point sensor based measurement. So we went to a small feedlot. This one had 300 cattle, so way smaller than that previous picture. It's kind of 50 by 70 meter size, so very small feedlot. But the point for doing it at this small feedlot was that we could take our system, which was in this trailer here, and have two measurement beam paths, one on one side, one on another side of the feedlot, so north and south sides of the feedlot. And then we could run a CRDS sensor where it was sampling on multiple points along each of these paths. We want to really get fluxes out of this, so we need to also know wind speed and direction, and then in addition to the gas concentrations that are measured along these paths, we need to do some sort of flux estimation, so we use an inverse dispersion model for doing that. Of course, field measurements have their own challenges, and so we had these fibers taking light to each of these telescopes, and rodents, even though they were in tubes, rodents decided that fibers are apparently tasty, or they decided that they at least wanted to sabotage the experiment. I don't know. But despite their best efforts, we were still able to get several months of data out of this system. So this is an example of partial days worth of data. And so in this case, we had wind coming out of kind of this direction, so blowing across the south path, and then over the animals, and then through the north path. This was done out in Kansas, where apparently winds are much more stable than in Colorado. If we tried to do this sort of plot for winds in Colorado, you would see, we've tried to do these measurements before, and the wind just flips around every like 2 or 3 minutes, and it's a total pain. Kansas, apparently the wind just sits in one direction, so that was great. What you see in the second panel then is the north-south in red and the south path in blue, both the CRDS sampling in kind of the open and the solid being our DCS sampling, and you see they agree quite well, which is not too surprising given that the CRDS was sampling from multiple points, and it's a 50-meter distance, so it really was, approximating what we should see. So that was great, and then we were able to do flux estimations using both of these. Since the concentrations agree, the fluxes also agree. And we can look over time now and look at what the diurnal profile of fluxes are. And one interesting thing is you see it starts to peak go up in the morning as the animals wake up, and then also they're fed both in the morning and in the afternoon. And so you see it continue to rise and then fall back overnight. Most inventories use kind of a single value that don't have this diurnal profile in them. If you compare to what, say, the IPCC inventory is, the average agrees quite well, but this diurnal profile could affect what you see at different times of day if you're doing measurements only at certain times of day. Cool thing with the DCS, though, is that we're also able to measure ammonia. And so this is a case where the open path measurements, now allow us to have measurements of these like sticky and reactive gases. So this wouldn't have been possible with the Picaro system there because of the long tubing necessary to run the multiple sample points. And so we can do the same sort of thing where, we had the wind, same direction again, and then ammonia on north and south paths, and look at the flux of ammonia as well. Now I said we wanted to do this for grazing. So here's kind of the idea of how this would work, is that we have multiple reflectors out in a field and a couple of telescope systems, kind of like the feedlot, but in a bigger kind of arrangement. And then multiple reflectors allows us to target which region of the field we're looking at. And, the cows are out over here grazing. And first thing we want to be able to do, though, is test it. So, we took stuff out to a trailer. This is a picture of what kind of the new generation of these near-infrared greenhouse gas DCS systems look like. And then, again, light goes out these telescopes here. Cows are kind of difficult to work with. So, they move around as desired. So instead, we set up some controlled cows initially, which are basically some tubes running to a bunch of outlets that are at approximately cow height. And this is what the measurements from controlled cows look like. So we, again, have the south path and north path, but now these are longer measurement paths, several hundred meters instead of the 50 meters in the previous one. And you see wind coming again, this direction, and you see north path showing enhancements relative to the south path during this time period after basically 1600. And that is when we turned on the gas release to simulate basically 27 head of cattle in this area. And then you can, again, run the inverse dispersion model and compare to our known releases that we were doing, and you get quite good agreement. So that shows that, we can, in this sort of setup, you can measure fluxes from, 27 head of cattle fairly reliably. So now the question is, can we do it actually with real cattle? So we actually kept stuff at the same site when they started grazing the animals. And here's an example set of data where if you start to look, you see enhancements on the north path. The wind is out of the south. You see enhancements on the north path compared to the south path for a certain period of time. Like I said, cows do their own thing. So one of the challenges with this is we need to know where the cows are at. So we have a camera, and during this time period, we can say that there was a herd of cattle in this area. But in order to do the inverse dispersion model, we need to know better where the cattle are at. So we're working on trying to figure out how to best track the cattle in the field in order to actually get good flux estimates with the inverse dispersion model, because it matters if they're next to this beam path or if they're next to this beam path, the enhancement that you see differs. All right, so moving on from cattle operations, we now want to look at kind of more regional methane emissions and apportioning sources in a variety of different source sectors. In order to do this, we need to be able to measure source-specific tracers. So ammonia is a tracer for cattle, but let's, we need something to trace, say, oil and gas. And so for that, we wanted to be able to measure ethane. Unfortunately, ethane doesn't have strong absorption in the near infrared, where our laser system was initially based. So we needed to move to a different wavelength region. In this case, we wanted to look more at the infrared sort of fundamental vibrational transitions, which are much stronger. And so we can move to kind of this 3000 wave number, 3 to 4 micron region, where you get strong CH fundamental vibrations. This now makes the laser system a little more complicated. So we had to figure out how to get our lasers, which were engineered for the field, but don't emit light at this wavelength region, to actually emit light. So what we do is we take one of these lasers and split it and do some fancy nonlinear optics tricks to get 1 micron and 1.5 micron light that we can then mix in some more nonlinear optics to do difference frequency generation to get light out at 3 microns. Long story short is that we kind of now have a source that can cover this 3 to 4 micron, fairly broad wavelength region with reasonable power in a transportable and fieldable configuration, which means something like this. So it's not as small as the previous pictures you were seeing, but that's because there's more optics that are required for it. So this is now all the optics required for converting to the mid-infrared. And it's still scientist level engineering, but it is stable enough to be able to run in field situations. So this is what an example spectrum looks like. See lots and lots of strong absorption. A lot of this is from water, and then actually in this wavelength region, it's from deuterated water, so HDO. And then absorption from methane, ethane, and propane are all in there, easily detectable. We get some other VOCs are measurable. We can get formaldehyde and some various other gases. So now, in order to do this sector source apportionment, what do we want to do? So we want to be able to observe sector apportioned methane, which we're going to do with multiple tracer gases. And we compare it then basically to predicted sector apportioned methane, which we're going to do with an atmospheric dispersion model. So in this case, sort of a backward Lagrangian calculate footprints, convolve it with some sort of gridded inventory, and compare that to the mean diurnal mixing ratios of this source apportioned methane. So we take the methane, we say how much methane is coming from oil and gas, how much methane is coming from agriculture, get diurnal profiles, look only at the midday times when these models actually work reasonably well, and then compare that to what the models predict. So for observing the source apportioned methane, I already showed you the system, but where are we doing these measurements? We went out to the Platteville Atmospheric Observatory. For For those of you who don't know, that's basically kind of northeast of Boulder. It's in the middle of Weld County, so in the middle of the Wattenberg Field. So that's this background is showing kind of the well density. So in the middle of oil and gas operations. And then there's many confined animal feeding operations with a variety of different cattle, dairy, poultry, few sheep, but not too many sheep around in that area. But it's this, really heterogeneous mix of agricultural sources of these cattle operations and these oil and gas sources. We had our systems again running in our van with telescopes sitting outside, and there's kind of the multiple systems running in the van now. Took data for about 3.5 months. This is a shorter time period. Fit a variety of different gases, formaldehyde, didn't see much HCl, but we can fit it. Methane and ethane into OCO2, water isotope logs, path average temperature. Mostly I'll focus on right now the methane and ethane, and then we adding ammonia. For these ammonia measurements, we actually used an ammonia picaro because we were testing our ammonia measurements for low concentrations, and we had the picaro running at the same time, so we just used that. So this is what our time series now of methane, ethane, and ammonia looks like. But now there's a question of how do you apportion this methane over this long time period? So you can try to do a regression type analysis. Normally this is done over short time periods where you can reasonably assume that the regression coefficients don't change. You can try to do a rolling regression, but you now have a big question of what rolling window you use. And that can affect the results a little bit. What we ended up doing is what's called a dynamic linear model. So basically we're doing this regression where you're fitting the methane with background term proportional to ethane and term proportional to ammonia. But you're letting these coefficients evolve over time. So you're using his previous information and then error, knowledge of kind of the errors, and you're letting the coefficients evolve as a function of time. As an example, here's sort of a few different plume events that we see. And so the oil and gas, the total methane that we saw is in black. The oil and gas attributed is now in blue, so that's the regression coefficient times the ethane, and then regression coefficient times the ammonia gives us the agricultural oil and gas, or the agricultural methane. And the reason, again, for doing this dynamic linear model, we can look at kind of the regression coefficients as a function of time, and you see, the methane to ethane somewhat spread out as we're picking up different sources, but some, fairly tightly correlated. But if you look over the entire time period, there's huge range, especially in the ammonia to methane. And that's because we pick up a variety of different sources. So chickens have a very different ammonia to methane ratio than dairy cattle, than beef cattle. And then also ammonia is a lot more sensitive to deposition and evolution rates and things like that. So there's just this wide range. So being able to let it fit over time allows us to extract kind of this total fraction that is the methane attributed to ag and to oil and gas without having to rely on sort of fixed regression coefficients. So from there, we can then do kind of an inverse analysis using dispersion model and inventories. So many of you know this much more than I do, so I'll just give a couple of details. We use the stilt model driven by meteorology from the high resolution rapid refresh because that's readily available, and 3-kilometer grids. We modeled footprints over kind of a 6x6 degree domain with either 0.1 degree or 3-kilometer resolution. We checked releasing several different numbers of particles, looking at both 24 and 48-hour back trajectories. And then we compared with, in the stilt model, there's a hyper-near field term that you can use. So we had a hyper-near field either on or off. Basically, that changes how the mixing is done within a single grid cell. For the final results, we used hyper-near field on. And so getting to the results, this is what we see. So this is now looking at oil and gas specifically. So we can pull an oil and gas specific methane emissions inventory. So in this case, this is the gridded EPA oil and gas terms. This is the prior from the inventory. Our inversion was mostly sensitive to basically this dotted region, so we can sum up the mean flux in that dotted region. And then the inversion sort of improves upon the prior to give you this posterior now emissions map, and then this is the difference between the two. And you see the mean flux, slight decrease, and maybe a bit of a shift in the spatial profile, which isn't too surprising given that this EPA used data basically from 2012. So it's not surprising that the distribution changes. Oil and gas operations have moved kind of around for where the active ones are, and the active ones are kind of closer to this side now. So it's not too surprising that it's shifted a little bit. What is interesting though is that this kind of mean flux in the region is very similar to the 2012 numbers, despite the fact that there's been 3-4 times increase in gas production in this whole region over this time period. So we can calculate an emissions intensity or emissions factor, which is methane emitted over kind of barrel of oil equivalent produced. So that's a combination of oil and gas produced, and start to compare now to other studies. One thing to note is that the other studies mostly all measure total methane, and they don't have ways of attributing it to oil and gas and agriculture specifically. So they measure total methane, and they have to use inventory values to extract out the contributions from ag, and then are left with what they think is the oil and gas contribution. But you see across these studies, which were done with aircraft and with satellites, a fairly consistent trend where this emissions factor has been dropping since kind of the early to mid 2010s. And that's conveniently also about when regulations started to take place in Colorado on new oil and gas operations. So there's a lot happening in Colorado on regulating emissions intensities from oil and gas operations. One thing to note is that it does seem to have plateaued. So that's something that, this is where repeat measurements years later are going to be necessary. And Colorado has new regulations where companies need to report their intensities, and Colorado needs to either verify or also sort of have total intensities for these basins that they can use as default values. So you need to be able to do this monitoring over years. Now for agriculture, there's a different story. So this is now the EPA agriculture. One funny thing is that, this is a very spread out distribution, because what they do is they attribute the agricultural emissions to kind of land use type based off of the total emissions estimated in the county and the number of animals and things like that. So the mean flux in our region is fairly small, but if we do the inversion, we get a huge mean flux in our region. And a huge change from the prior. Part of this is actually attributable to the fact that this land use type is not really how you should distribute emissions in Colorado. Pretty much all the cattle are in these confined animal feeding operations. So if we redistribute the EPA to now these confined animal feeding operations, this is what the prior should look like, we think. And then the posterior still produces higher fluxes, but less correction required to this prior. And why does it produce higher fluxes? That's uncertain. We need more measurements. Some of it could be the fact that we're using midday data. So I previously showed this diurnal profile that will affect the average versus the midday observations. Some of it could be a number of small operations that just don't report cattle to the state, and so then those don't get into the total head counts. We're also more sensitive to different animal types as in different regions of this area. So there could be an error on specific animal types, like chickens, for example. There was a huge chicken operations kind of up here. So we're still investigating this. All right, so the final thing I wanted to talk about in applications is looking at urban greenhouse gas emissions. So we did measurements actually a while ago now, where we had two paths from NIST. This 1 kilometer path that I showed you before, and then one that was a 3.5 kilometer path kind of across the city. And, we measured for a month and a half, and what we did is we didn't have the inversions set up at the time, so we just used a couple of days where the wind was cooperative and coming mostly out of the west, where you could treat this this path as really a clean background path. And used a simple Gaussian plume model to estimate traffic emissions in the city. Question is, though, can we, this 3.5 kilometers was really pushing what we could do. Can we do longer path lengths to try to observe larger areas? And so this is, what our setup normally looks like. I said we send light out to a reflecting mirror that sends it back to our telescope. But that really only works out to, maybe if we really push it 5 kilometers so far. And the reason for this is that we lose a lot of power as a function of distance. So the amount of power we get back basically scales as distance, 1 over distance to the 4th, which is incredibly unfavorable for the signal to noise ratio as you go to longer distances. So our solution is to try converting this to a one-way path where we take half of this telescope basically and put it out on the other end instead of having a reflecting mirror and have our data acquisition out over there. This now gives you basically a 1 over d squared power scaling, so you're much more favorable to longer distances. In addition to measuring larger, just going over longer paths, one of the thoughts is that these sorts of footprints are now much more relatable to satellite footprints. If you're measuring 5, 10 kilometer sort of paths, you're much more similar to what OCO2 and OCO3 are seeing and what you can see from a lot of the Earth observing satellites. You can also try to do sort of full cities, right? So 10 kilometers, I keep mentioning that number a little bit, but this is the scale of Boulder. So if you have a 10 kilometer measurement, you could really basically be measuring north to south on a city like Boulder. And we want to do this while maintaining the advantages of dual cone spectroscopy. So this high accuracy for measurements. So here's our test measurements over a 14 kilometer path from NIST out to Table Mountain, which is north of Boulder. So we send light from similar telescope as I showed previously along this path, and then we moved our receiving telescope to a dome over at Table Mountain. This is what an example spectrum looks like. You see now really strong absorption because we're going over a really long path of, again, the same CO2, methane, more CO2 bands, and a bunch of water scattered throughout. So we can fit that for temperature, pressure, water, CO2, methane. This is the fit now and the fit residuals. We see more sort of line shape errors, so that's something that's still under investigation. We can look at the sensitivity over this measurement path, and we get kind of part per billion level sensitivities for methane and sub-ppm level, sort of 1/10 of a percent level of background for both methane and CO2. That's already quite useful. One interesting thing, though, is that fractionally these sensitivities, or these sensitivities are basically very similar to the sensitivity we see over a 2 kilometer path, which doesn't make a whole lot of sense to us because the absorption is a lot stronger and our signal was actually fairly similar. So we're still trying to investigate, why we don't actually get better sensitivities over these paths. But it already is giving you 1/10 of a percent level measurements in 2-minute averaging times. So we operated this system for a couple of weeks. Here's fit to pressure, temperature, water, methane, and CO2 as a function of time. One thing to note about the pressure is that that's likely from calibration issues in Hytran, right? So if they have a slightly different broadening coefficient, that we would see that as a pressure error in our measurements. Everything else seems to agree quite nicely. You can look at the CO2 to methane correlations. Not too surprising, you see a wide range of correlation coefficients ranging from kind of 3.5 to 20 part per billion methane to ppm CO2. These correlation coefficients are kind of roughly in line with what people see from other cities, and they can give you a scaling of emissions, of kind of how much the methane emissions in your measurement area are different than the CO2 emissions, and thus relative scaling between two emissions inventories. Say. We can also do an inversion with this. So this is a CO2 inversion results. And what you see is that kind of, so this is the Boulder area, and you see larger emissions kind of in some of the urban areas, Boulder, south of Boulder, Longmont, areas where population has been changing. So if you can look at the city of Boulder, we see kind of compared to the FFDOS inventory, which is what we used for this, a factor of almost 2 difference in CO2. And then you can do the same thing for methane. And all this is with just a couple weeks of data. So it's kind of neat that we can get kind of these large areas in shorter periods of time because we're measuring over this long path. For methane, you see, again, increases in urban areas. And this is the Wattenberg field, where we already showed that, very similar, it's like slight decrease compared to the prior. So that's kind of consistent with what we saw earlier. The inventory predictions in the city of Boulder are way off. So we see huge difference in the methane for the city of Boulder. Now, city of Boulder in this case is 1 grid cell, so there's some uncertainties there, right? But we can also then compare with what the city thinks. So that was this EPA inventory, right? But the city is also producing their own inventory, so we can compare with what the city thinks, which is maybe a little more relevant. These numbers are also subject to uncertainty because the city doesn't break it out, doesn't really clearly identify what things are outside of the city limits versus inside the city limits. They do what's called scope 2 emissions. So we had to subtract off a bunch from what the city reports. So there's still some uncertainties there. They also don't split it off methane versus CO2. So we had to pull what we think was just the methane numbers. But what you see is a slight increase in the CO2 and a huge increase in the methane. So that already gives targets for what things to look at now in the future for kind of a longer term monitoring. And with that, I have now a couple slides kind of on where we're going. So I showed this already from our mid-infrared measurement system. You might wonder, hey, what about all the other gases that you can measure? So said we could measure water and deuterated water, so we can get this delta D of water. We looked at that a little bit, and that can give you information about kind of larger scale meteorology. Can also give you information about evapotranspiration type fluxes. We haven't done much more with that. And then we're also looking at formaldehydes, an interesting one that we can measure. So we can look at from this multiple month measurement campaign, the diurnal profiles of formaldehyde. You see this kind of slight U-shaped diurnal profile, which is indicative of primary sources, at least some primary sources, right? So this a U-shaped diurnal profile occurs when you have kind of constant sources that are getting trapped in the boundary layer as the boundary layer collapses, and so you get increases overnight, drop back as the boundary layer rises up during the day. We do see some evidence of secondary production, so the diurnal profile doesn't quite match what you would see from, say, CO2 or methane diurnal profiles. So we're still looking at splitting up, primary and secondary emissions. The primary emissions in this case, are probably coming from combustion from oil and natural gas operations in the area. And then we also see that it's correlated with methane and ethane, so that's why we're attributing it to this oil and natural gas. And then you can look at the formaldehyde to NO2. We don't measure NO2, but there were separate measurements of NO2 there, and start to look at the ozone formation regimes. And we have some more field measurements coming up or occurring or just occurred. So this is field measurements in New York, also hoping to go out to Salt Lake City next summer, looking at greenhouse gases and air quality. We want to do more with this scanning UAV system. And then looking at kind of larger other distributed sources, landfills, wastewater treatment plants, wetlands, things like this. Looking at ammonia, and I didn't really touch on it, but we can also measure N2O somewhat. And so looking at ammonia and N2O for agriculture. And then looking at mitigation measures. So doing these feedlot measurements, but as a function of feed of other mitigation measures. And then finally, we have kind of more of lab applications using the mid-infrared system, and then also extending to the fingerprint, the longer wave infrared, where you get more of the CO vibrational features to detect a wider variety of gases in more of a lab environment. And with that, I'll say thank you for listening. Happy to take questions, and just acknowledge the people who worked on this in the group.
Are there any questions for Kevin?
Thank you for your presentation. My first question is, when you show the difference between the posterior and the prior in both of your parts of your presentation, you didn't show any of the uncertainty. So we're not sure if that increase or decrease of the posterior emissions is within the range of uncertainty.
That is correct. So couple of things. One, for this inversion, we're actually doing a slightly different inversion methodology where we're using simulated annealing, and we're actually trying to understand how to get uncertainties from the simulated annealing inversions. So that's still kind of hot off the presses data where we're really trying to understand that better. We do have uncertainty numbers on the mean fluxes, and the uncertainties from the inventory are just large, and so it's really hard to say. So, we use the numbers that the EPA is in the gridded Massacres inventory from the EPA, and if you propagate their uncertainties through, you just get rather large uncertainty values for the inventory.
But I mean for the posterior analysis, for the uncertainty from the inversions.
Yeah, okay. Right, so we have uncertainty on the mean flux, which came from the inversion. We have numbers for, so the mean square error decreases by comparing the prior observations with the observations and posterior with the observations. The mean squared error showed kind of a factor of 2 improvement with a lot less scatter. So I could show, right. So this is this kind of shows it anyway. The prior gave kind of this wide scatter, in the posterior improved on that. So we can give uncertainties on the posterior. I don't know, I don't have an uncertainty map for the gridded ones produced right now, or at least not in the presentation.
Can I have one more question? Yes, this is a very simple question. I had just a very small doubt. If you show the map of the prior and the posterior and the green map, if you show that slide, I just was not clear because Your prior was 2012, right?
Correct.
But your measurements were in which year?
The measurements were in 2022.
So why you didn't use an updated version to compare with, because you are assimilating 2022 observations and then using
Yes.
a prior of 2012, and obviously you will have, oh, there was a decrease because the trend of methane is decreasing the emissions according to the official data. So why there was not available updated emissions inventory to use as a prior? Thank you.
So this was actually the only gridded inventory for methane that we could find at the time. So it was, so the EPA produces inventories that are on kind of the county level fairly regularly, but they didn't produce gridded inventories regularly. And so, for the prior, we needed a gridded inventory. The state also doesn't have a gridded inventory. And so the only one available at the time was this Massacre's 2016 gridded EPA inventory, which used 2012 data for their gridding. There is a new one out now that just came out recently, and it's similar, very similar, but I don't have the inversion done with that one.
Hey, Kevin, thanks for the presentation. I was wondering about just the stability of the system. So when you go and deploy this instrument, do you have to be there the whole time, or is it stable enough that you can leave it for a long period of time?
Yeah, so we usually basically run it, we deploy it, and then we run it remotely. So for the 3-month measurement out at Platteville, we actually had to go out there to get data from it because we didn't have a good enough internet connection to get our data back. So we went out there about once a week to get data from that one. But the actual instrument just sat there and ran, and we could check up on it remotely. So for the most part, it's pretty stable. Still some hands-on necessary every once in a while, but.
Any other questions from the room?
I was just wondering how you treat natural CO2 fluxes in your inversions. And the side question would be trying to measure natural fluxes also, not just urban emissions.
Yeah, so the way we treat the fluxes in the inversion for CO2 is that we basically have done measurements when there's not much biosphere contributions. So, yeah, exactly. Everything's been in fall, winter. Oh, yes, small, but yes. That is also why we mostly focused on methane. So yeah, trying to understand the biosphere is something we want to look more at, but is very complicated. I think to your point, measuring, one of the nice capabilities is being able to measure these distributed fluxes, and so we are looking at how to try to do some measurements of biosphere, kind of split up biosphere and kind of monitor one site, or for methane, looking at wetlands or things like this. But we don't have any measurements done on that yet.
Any other questions from the room or online?
Thanks for the presentation. I was wondering, how expensive was it, the 2 different versions of the sensor that you had, and if the sensors are available for field campaign or people can request them?
Yeah, good questions. I would say kind of the near infrared methane CO2 system at this point would probably commercially cost $100 to $150K. We have been building up some of these systems and happy to collaborate on field campaigns. We don't have, we have a few systems basically. We also need more people to to run them, but we're definitely happy to collaborate on campaigns, and are fairly flexible in kind of what we work on.
All right. Well, if there aren't any questions, let's thank Kevin again.